So first we're going to start with partial fraction decomposition. It's not actually something you necessarily cover in class, but it's needed to do the inverse Laplace transformations. Like this that's right here. This is not going to be something you're going to have on your table. So you're going to need to break it up. But the good news is you can break it up. Alright, so that's the good news. We can break it up into stuff that is in our table. So what we'll do here is we want to factor out the denominator. So this numerator is going to stay the same. So we want to break it up into something we can do here. So s squared plus 9 times s. So now the bottom being s squared plus 9, we have that in our Laplace sheet, and 1 over s we have that. So what we'll do here is for each separate thing in the denominator, we're going to have a different numerator, and we're just going to leave it as a's and b's and unknown variables right now. So as plus b over s squared plus 9. Now this is kind of one of those rules. If you have a polynomial you can't factor out, like s squared plus 9, it doesn't have real roots. It has complex roots, and we can't do that. Okay, we have to have we're gonna have to put on the top as plus b. So that's what happens if you have a denominator that cannot be a polynomial that cannot be factored out. But other things, we just have it as one variable over the other one. So c over s. So now what we'll do is we'll multiply by the denominator the whole thing. So here we're going to multiply this side by s squared plus 9 times s, multiply this side by s squared plus 9 times s. The denominator is going to cancel. The denominator is going to cancel out on this side, and then we're going to be left with s plus 1 equals as plus b times s plus c times s squared plus 9. Now here we're gonna have to we can use a thing called killer x's to get rid of the to find one of them. Killer x's pretty much means we plug in a number for s. So let's say at s equals 0, this term's gonna go away, right? Because 0 times anything is 0. So we're left with 1 equals 9c, because this is a 0, so we get that, or c equals 1/9. Okay, now we can't do that for a or b, because the s squared will never be negative. So what we'll have to do is you can either plug in two other numbers, which is totally possible, or you can use a method called shopping cart. Okay, so what this does is we're going to distribute everything out. So as squared plus bs plus cs squared plus 9. Now we're going to color code this stuff because that makes life easier. So all the reds, so all the s terms, which are the reds, match up. Okay, now all the coefficient terms have to match up too. So sorry, there should be 9c. Okay, because I just struggled. Okay, so all the coefficients have to match up. Now you don't see an s squared on this side, but technically there is a 0s squared. Okay, so we're gonna put that. All these are gonna set equal to each other. So we're gonna have 0s squared equals as squared plus cs squared. Okay, the sum of those terms of these have to equal 0s squared because they're the only ones with s squared. And now let's do the s equals bs, and lastly we have 1 equals 9c. Now if you see, we've got the same answer, 1 equals 9c or c equals 1/9. So that's like how it works, right? So here we get c equals 1/9 on the red one, or the s term. The s's are going to cancel out, and I'm left with 1 equals b, or b equals 1. And now on the green, or the s squared terms, we're going to be left with if we divide by s squared, we're left with 0 equals a plus c. We know what c equals, so a equals negative c, which equals negative 1/9. Alright, and now we can finally plug all this stuff in. Now our original equation, so f of s is going to be what we just plug in our a, b's, and c's. So it's going to be negative 1/9 s plus b. B is 1 over s squared plus 9 plus c, which is 1/9 over s. And if you guys know, this is just going to be a cosine and a sine term over here, and this is just going to be a normal term when we do the inverse Laplace. That's what we covered last time. So that's how you do that. Moving on, let's do another one real quick, a little bit crazier, and it's going to explain another funny rule, not funny rule, but another rule that exists. So s squared plus 2s plus 3 all over s squared times s squared plus 3. Okay, so now remember we have a over s squared, but when we have a squared term like an s squared on its own, we have to break it down all the way. So we're going to have a b over s, and remember we have a polynomial we can't factor out. It's going to be cs plus d all over s squared plus 9. Now we multiply both sides by the denominator, and we get, right, the denominators cancel out, and we're left with s squared plus 2s plus 3 equals a s squared plus 3 plus bs s squared plus 3 plus cs plus d. It looks kind of nasty. S squared. So now if you see, if we plug in a 0, we'll get rid of b, c, and d, and we can solve for a. So at s equals 0, we're left with 3 equals 3a. Everything else cancels out, gets rid of, so a equals 1. Sweet. That is the only killer s we can use. So now we're going to have to do shopping cart. So let's just factor everything out. As squared plus 3a plus bs cubed plus 3bs plus cs cubed plus ds squared. And now we're gonna match everything up to each other. So technically here we have a 0s squared cubed, sorry. We have a 0s cubed term right here, which means that now we can match it up. So our 0s cubed has to go with our bs cubed and our cs cubed. Our s squared term has to go with our as squared and our ds squared. Our 2s term has to go with the 3bs term. And the 3 term has to go with our 3a term. So here we have 3 equals 3a, or just like we got before, a equals 1. Maybe we should just ditch the other method and just use this one. And we have 2s equals 3bs. Okay. So now when we divide by s, we're left with 2 equals 3b, or b equals 2/3. Alright. Now we get s squared equals as squared plus ds squared, or 1 equals a plus d. We know what a is, so therefore d must be 0. Right. Subtract it over. Alright. And lastly, our s squared, s cubed term, has to equal bs cubed plus cs cubed. And this will give us, if we divide it out, we're left with 0 equals b plus c. We know what b is. B is 2/3, so then c must be negative 2/3. And now we just plug all that back into our original equation, which is up here, and we're left with f of s equals a, which is 1 over s squared, plus b, which is 2/3 over s plus cs plus d. So c is negative 2/3 s, and d was 0, so we don't have to write that down anymore. Alright, so this is what we end up getting right here. And from there we can use the Laplace sheet and easily go to the x domain again. So a piecewise function is any function that has more than one part to it, where different bounds at different equations are what matter. And what we'll see here is that we have to, well, there's a way to do these. So first you need to memorize something. It's first minus first u of x minus c plus second u of x minus c. Now this first and second refers to lines. So what this means is we're going to have 2x minus 2x u of x minus c. And c is always the upper bound here. So this is c. X minus 3 plus second, which is negative 1 plus x u of x minus 3. Alright, now here's where it gets a little funny. And here's where most people get lost. So pay attention. What happens here is, okay, first of all, first thing you need to know is this u of x minus c never factors distributes out, okay? So those always stick together, the u of x minus c. So don't ever mess with that. Now what we do need is every term has to be in the form of x minus c, u of x minus c, so that we can Laplace it. Okay, so that's kind of how that works. So first, let's just distribute in combined like terms, because it probably make our life easier. So minus 2x u x minus 3 minus u of x minus 3 plus x u of x minus 3, or 2x minus x u of x minus 3, because those combine, minus u of x minus 3. Now remember, we need it in the form of x minus c to be able to do it. So this is how we're going to do it. So here we're going to do x minus what we want, so x minus 3 plus 3. Okay, so we're adding by 0, so we're not changing anything. And all this minus u of x minus 3. Alright, and now what we'll do is we're going to group the one we want. We want x minus c, and now we'll distribute. So we're left with 2x minus x minus 3 u of x minus 3 plus 3 u of x minus 3. Sorry, minus 3, because of this negative. See, this negative goes here, and it goes here, and then we have to tag along that u. Minus u of x minus 3. Alright, so this gives us 2x minus x minus 3, which is what we wanted to begin with. It's just the way we have to Laplace it when it's a piecewise. Alright, now we can actually take the Laplace transformation of this. So the Laplace transformation of this is going to be 2, so just like normal, this has no u, so you Laplace it like normal, so 2 over s squared. Now this one, the reason we had it in the form of x minus c, u of x minus c, now we can treat this as an x. We can Laplace it as if it was an x. So this will mean this is going to be 1 over s squared. Now, another thing, when you see a u, you Laplace everything in front of it like normal, and then you just tag along e to the negative cs. Okay? In this case, e to the negative 3s. And now you Laplace the negative 4 like normal, so negative 4 over s, and then you just tag along e to the negative 3s. And that is how you get the inverse Laplace, the Laplace of the piecewise. What we're going to use Laplace to. So first minus first plus second is the main thing, and then remember that you need to get it in the form of u of x minus c. It's x minus c times u of x minus c to be able to Laplace it. Alright, let's try another one out for size. So here, again, it's going to be first minus first u of x minus c, which in this case is 3, plus second, so negative 4 plus x u of x minus c, which is 3 in this time. This this case. So let's distribute just to make our life a little easier. Minus 4u of x minus c plus x u of x minus c. Alright, so 2x minus x u of x minus 3 minus 4 u of x minus c. Now, remember, we need this to be in the form of x minus 3. So what we'll do is x minus 3 plus 3, we're literally adding 0. Okay. And now we group these together, distribute this through. We're left with 2x minus x minus 3 u of x minus 3 minus 3 u of x minus 3 minus 4 u of x minus 3. And we're left with 2x minus x minus 3 u of x minus 3 minus 7 u of x minus 3. And now we can take the Laplace transformation, left with 2 over s squared minus, we can treat this as an x, so that's what we'll do. So this will be 1 over s squared, and since there's an e, you just tag along the e to negative 3s, minus 7 over s, and now you tag along the e to negative 3s. And that's how you do the piecewise. Alright? This will be the piecewise of a Laplace of a piecewise. Versus Laplace of a piecewise. I think these are actually easier. So first, let's just take the inverse Laplace real quick, and we'll see that it's not that bad. So this, if y'all remember, or if y'all know from the chart, it's going to be negative 3x. Okay. Now, if there's an e to the negative whatever, we know that that means that it had a u tagged along it from doing the Laplace transform of a piecewise. So that means that this stuff in front, this is negative 3x. But remember, when it's in the form of x or e, when the u's tagged along to the end, it's x minus c. In this case, it's 2. X minus 2 u of x minus 2. Okay, because remember, it has to be in this form to be able to Laplace it. So when we inverse Laplace, it's going to go back into this form. And then this is going to be minus 4, and if you remember, this is e. This is e to the negative 2x. But remember, since it has the e to the negative 2s already, we have to, every x is going to be in the form of x minus c, which in this case is x minus 2. How do I know it's x minus 2? How do I know that's our c? Because that's our power up here on the e. Okay, so that, and then u of x minus 2. So now, to do our function here, f of x is going to be, so everything without a u, this thing right here, is going to be our first line. Because if you remember, it's first minus first u of x plus second u of x. So everything without a u is our first line. And our bound is going to be from 0 less than less than or equal to 2, because it's our c, right? So then this is going to be otherwise, and now we have to find our second line. So remember, it's first minus first u of x minus c plus second u of x minus c. So a way to solve for it is, say we ignore this u stuff. What'll happen? The first will cancel out and we're left with the second. So that's what we're going to do. We're just going to ignore our u's, and we're going to have negative 3x minus 3x plus 6 minus, I'm just distributing everything out, negative 2x plus 4. Okay? Now we combine our like terms, we're left with negative 6x plus 6 minus 4 to negative 2x plus 4. And this is our second line. So it's not that bad. It's not bad at all. So we're left with, I guess if we want to do it in order, it'd be 6 minus 6 x minus 4e to the negative 2x plus 4. And this is going to be a multiple choice, so you're going to really have to look at how they format it, but it's pretty straightforward. Alright, let's do another one. So in this case, we'll do the same thing, do the inverse of Laplace. That's just 4, if we remember for the table. This is 3x, so it's going to be 3, but remember x has to be x minus c because of the u, and our c is 3 because of that power. Alright, and then this guy is going to be 4e to the 2x, but remember x has to be in the form of x minus 3 when it has u at the end. Every x has to be in that form. And now our function is going to be 4 from 0 less than or equal to x less than or equal to 3, and then now we're just going to ignore our u's and we're going to combine. So 4 plus 3x minus 9 plus 4e to the 2x minus 6, or negative 5 plus 3x plus 4e to the 2x minus 6. So negative 5 plus 3x plus 4e to the 2x e to 2x minus 6, and that's otherwise. So there you go. That's how you do the inverse Laplace of a piecewise. Alright, so the last thing that's kind of a curveball I threw like a year ago, I think, is this part. So it's if they give you a set of particular solutions, how can you find the fundamental set and the general solution? So that sounds kind of confusing. It's not that bad. So for every particular solution to the same differential equation, the thing that's repeated is our particular solution. Okay, that means like the particular solution. Sometimes I don't know if you remember, in our variation of parameters, we sometimes get a part of our general solution in there and we can just ignore it. Well, that's kind of what happened here. So everything that's repeated, that's your actual particular solution. So what's repeated every time is e to the x squared e to the 2x. So that's our actual z term. Now our fundamental set of solutions is going to be everything else that wasn't repeated. So our y1 we can just see that is x cubed because of this term right here. And then our y2 would be this one because it's a different power, so it would be x. Alright, so that's how we find the fundamental set of solutions, so y1 and y2. Now the general solution is going to be c1 x cubed plus c2x plus our z term, which is x squared e to the 2x. It's not bad at all, it's just something you need to see before you go in there. Let's just do another one real quick. So remember, everything that's repeated is going to be our actual particular solution. So z is x e to the 3x because that's the only thing that's repeated every time, and our y1 then is everything. This is what's not repeated, so x cubed, and our y2 is going to be x to the 5th. Now that's part I. Double I is going to be y equals c1 y1 plus c2 y2 plus our z term, which in this case is x e to the 3x. Alright, so it's pretty straightforward, and that is everything you need to know for the exam. Good luck.